Okay, so last time we finished our lecture with a quiz. Let's start by solving the quiz. A conducting sphere of radius r, let me try to plot one, is charged with a total charge q. Now, when I see the word conducting, what should I think? I should think that charges are free to move inside this conductor. And what will they do? They'll actually go to the surface, right? And this is what part A asks. What's the surface charge density on the surface of the sphere? Well, I have a total of q charge. The total surface area of the sphere is 4 pi r squared. So here I have the surface charge density, which is q over 4 pi r squared. Good. Now, find and plot the magnitude of the electric field inside and outside the sphere. So one part of this question I can actually answer right away. And which part is that? That's the inside of the sphere. What's the electric field inside the sphere? Inside a conductor is 0. That's pretty much how we define the conductor. So for r less than r, electric field is exactly equal to 0. Now, how about on the outside? This is a symmetric enough problem. So here is my sphere. It has spherical symmetry. Charges are distributed symmetrically. So what's the best way to find the electric field in this problem? It's to use Gauss's law. So what I'll do is I'll take a Gaussian surface of radius small r, and I'll say E dot dA is equal to Q in over epsilon 0. Clearly, all of my charge is inside the Gaussian surface, so Q in is equal to Q. How about E dot dA? By spherical symmetry, E is parallel to dA everywhere on the surface. So I can say E dot dA is magnitude of E integral dA. And that's the total surface of the Gaussian sphere, 4 pi small r squared. So now I can equate this to Q over epsilon 0. Not surprisingly, when I have the spherical charge distribution, electric field is just like the electric field of a point charge. And that is true for r larger than r. Then, how do I calculate the potential? From the electric field. And it's actually quite simple, right? That's actually how we define the potential. So potential difference between 2 points, let me write it as delta V, is from initial point to final point E dot dl with a minus sign. And what did this minus sign say? It said if you're going uphill, if you're going to a higher potential, you must be opposing the electric field. So here I know E is a function of r, right? Just the usual Coulomb's law. So the problem though is that defines the potential difference between 2 points. So I need a point, I need to fix some reference point. And I'm going to say this charge is in a limited region. It should have no influence at infinity. So when I go infinitely far away from my charges, the potential is 0. And that's an approximation. Well, it's not an approximation. That's an assumption we can make in certain problems. And actually just today we are going to see counterexamples. We are going to see examples where we cannot take the potential at infinity to be 0. Okay, if I take this to be 0, let's see, then potential at, let's say, R1 would be integral from infinity to R1 Q over 4 pi epsilon 0 R square dr. Now, what's the integral? These are constants. I'm taking them out. The integral is minus 1 over r at r1 and infinity. But remember, I had this minus sign, which I have to put in front. So overall, this is going to give me q over 4 pi epsilon 0 r on the outside. Am I surprised? No. Why should I be surprised? If the electric field is just like a point charge, potential should also be just like the point charge. Right, but how about on the inside? On the inside, electric field is 0. And what was electric field? If I actually write this in terms of components, the components of the electric fields were partial derivatives of the potential. If the electric field is 0, all of its components are 0, which means the derivatives in every direction for potential is 0. Then potential is a constant on the inside. All right? Then what's the value of this constant? Let me actually try to plot these on the figure. I said electric field is 0, and then like a point charge on the outside, so it's q over 4 pi epsilon 0 r square. So the maximum value is q over 4 pi epsilon 0 r square. And the potential is again like a point charge on the outside, q over 4 pi epsilon 0 r. Maybe it's dropping a little bit more slowly, but it's a constant on the inside. So the value of this constant is q over 4 pi epsilon 0 capital R. So V inside is q over 4 pi epsilon 0. And all of a conductor, remember, charges are not flowing inside the conductor. What does that mean? It means all the points of a conductor are at the same potential. And we found for a sphere it's charged with q, the value of potential is q over 4 pi epsilon 0 r. Now maybe I can clear up something from your high school experience. One of the most favorite questions in high school physics is that if I have a sphere with radius r1 that's charged with q, and I take another sphere with radius r2, I let them touch each other and then go their separate ways. So the question is, what are the charges after they touch? Now, in high school, the way this problem is solved is that people state, well, probably your physics teacher stated that the charge is distributed proportional to the radii. So this must be r1 over r1 plus r2 times q, and this must be r2 divided by r1 plus r2. But what's the physical principle behind that? Why do charges flow from r1 to r2, from the first sphere to the second sphere? Because they are not at the same potential. So initially, the potential here is going to be q over 4 pi epsilon 0 r1 while the potential here is 0 because there is no charge, and the charges will keep flowing until the two spheres are at the same potential, which means Q1 over R1 must be equal to Q2 over R2. That's why the charges are split proportional to the radii of the spheres. So there is no magic involved in that. Okay, let's solve one more problem. Let's take our old friend, the infinite wire. Okay, which is charged with lambda charge density. So infinite wire, charge density lambda. Find V of R, the potential, the electric potential, as a function of distance from the wire. So if I'm a distance r away, what's the potential here? Now, we've learned two methods to calculate the potential. I can either break up this infinite line into small sections and then integrate over from minus infinity to plus infinity. That's the first way. Or I can first calculate the electric field and then find potential by integration. Now, in this problem, calculating the electric field is extremely easy. Why? Because it's very symmetric. I can actually use Gauss's law. So my solution will be consist of two steps. First, I'll use Gauss's law to find E, and then integrate E to find V. Right? Now, how do I use Gauss's law for this problem? What kind of symmetry does this system have? It has cylindrical symmetry. So I immediately take a Gauss surface, which is a cylinder. The radius of the Gauss surface is smaller, and let's take the height to be L. Now, we have to calculate the flux through this Gauss surface. There are three surfaces here: top surface, bottom surface, and the sides. So let me separate E dot dA into three parts. E dot dA on the top, E dot dA at the bottom, and E dot dA on the side. But now, which way is dA? dA is always pointing outward. So it's in the positive z direction on the top surface, negative z direction on the bottom surface, and on the sides, it's basically perpendicular to the wire. Now, how about the electric field? Electric field, can the electric field choose between up or down? There are equal amount of charges above any point and below any point. So it's actually an infinite system, right? So the only way electric field can point is perpendicular to the wire. It will always be perpendicular to the wire. So on the top and bottom surfaces, E is perpendicular to dA. So E dot dA is 0. There is no contribution from this surface. On the side surface, though, E is parallel to dA. So this is going to be E magnitude dA. Now dA magnitude, which is going to be the side area of my Gauss surface, which is going to be 2 pi r times L. That's good. We have calculated the left-hand side of Gauss' law. How about the right-hand side? I need to find Q in. So here is my Gauss surface. The charges are exactly on the z-axis, and only the charges inside the Gauss surface concern me, which is q in. So can you tell me the amount q in? Well, only a section of size L is within the Gauss surface, so it should be L times lambda. Now I know q in, I know E dot dA, so I can write Gauss's law. Q in over epsilon 0. E dot dA I just calculated to be 2 pi RL. Magnitude of E, Q in is lambda times L divided by epsilon 0. So I find E magnitude to be L's cancelled, and I'm relieved because L was something I invented. It wasn't given in the problem. Help me solve it though. 2 pi epsilon 0 R. Good, so I've accomplished my first step. But now I have to integrate E to find V. Let's say I want to find the potential difference between 2 points. I'm actually going from R1 to R2. So let me try to calculate delta V, which is going to be V at R2 minus V at R1. What was my rule? It's going to be minus integral E of R dr in this case, from R1 to R2. And E of R I've just found is minus lambda over 2 pi epsilon 0 R dr from R1 to R2. So this is going to be, these are constants, lambda over 2, 0. What's the integral 1 over R dr? Now it's ln, right? So minus lambda 2 pi epsilon 0 ln R2 minus ln R1. But ln A minus ln B is ln A over B. So I can maybe write this as lambda over 2 pi epsilon 0 ln R1 over R2. First of all, let's check if I'm doing something correctly. V of R2 minus V of R1. Let's check the signs first. R2 is farther away from my line. So do I expect it to be at a higher potential or a lower potential? I certainly expect to be at a lower potential, because if I leave its charge at R1, it will actually accelerate towards R2 because of the electrical force. So I would expect this to be less than 0. V of R2 is less than V of R1. Is it less than 0? Remember, ln 1 is 0, and ln anything ln x is less than 0 if x is less than 1, right? And in this case, that's certainly the case. So it looks like a correct formula. Now, I need to choose a reference point. And you may be wondering why I'm actually just looking at the potential difference. Why didn't I choose a reference point? More specifically, why did I not choose the potential at infinity to be 0? Right? That's how we approach the problems until now. The problem is, in this example, I have a charge density that's going to infinity. And if I actually put charges at infinity, I cannot be sure that potential at infinity is 0. So because there are charges at infinity, we cannot choose v at infinity to be 0. So we cannot do that. What do we do? Well, choose any reference point you want. Okay, I'm going to choose an r, let's say 1 meter. You can take any scale you want and set it to 0. Then for any point, what's our rule? V of r minus v of r. I'm just rewriting the formula above. Instead of r2, I wrote capital R. Instead of r1, I wrote small r. So if I choose this to be 0, v of r is apparently lambda over 2 pi epsilon 0 ln r divided by r. So we found the potential. I hope this is clear. Now, let's quickly move on to another example. You remember we could use Gauss's law in 3 kinds of symmetric situations. Either we would have spherical symmetry, or we will have some infinite distribution in one direction, and I'll use cylindrical symmetry, or I'll have infinite distribution in 2 directions, and I'll have planar symmetry. So we've done the spherical case and cylindrical case. Let's solve a problem about the planar case. Okay. A slab of thickness d, and let's say an infinite slab of thickness d, has uniform charge density rho. Find the potential inside and outside this slab. Okay, so what does the question ask? Well, it says if I have, let me first put my coordinate frame here. So here I have a slab which is infinite Okay, I could probably draw this better. So it's actually going to infinity in these 4 directions, but its thickness is d, and it has uniform charge density rho on the inside. I'm terrible at drawing 3-dimensional figures and thinking maybe 3-dimensionally, but I'm actually much better if I take a side view. Okay, let me draw a side view here. So if this is my z-axis, this is my x-axis, my slab would be something like this. And let me choose my coordinates so that the slab is between plus d over 2 and minus d over 2. Well, the distance is d over 2, so in the z-axis. Now, how do I find the electric field inside and outside this slab? This is quite symmetric. So what do I need to do? I need to define a Gauss surface. So I'm going to do it in 2 steps. First, find E outside. So how am I going to do it? Because of this planar symmetry, I will actually use, and I'll take a Gauss surface, which is a cylinder, which is symmetric. So it cuts the surface, it cuts the slab, but it's symmetric with respect to up and down reflection. Let's say the radius of the cylinder is r, and so if this is z, this is going to be 2z. The length of the cylinder is going to be 2z. Again, maybe it doesn't look so nice on the three-dimensional plot. So if I look at the system from the side, this is what I'm doing. The Gauss surface is symmetric, so its height is 2z, and its radius is r. Now, by symmetry, which way is the electric field in this problem? Electric field, so if this is my slab, electric field cannot choose a direction within the plane. It cannot point to north, south, east, west. It has to always point away from the plane, right? So the electric field will be away from the plane. It will be away from the plane on the sides as well. On the other side, though, it's going to reverse the direction. So electric field will be pointing. If this is my plane, it's pointing down when I'm below the plane. If I'm above the plane, it's pointing up. So very quickly, let's calculate E dot dA. Again, I have E dot dA on the top, E dot dA on the bottom, and E dot dA on the side. But on the side, dA and E are perpendicular. So on the side, I can comfortably say that flux is 0. On the top and the bottom, well, then E is parallel to dA. So, is my computer freezing out? Okay. E dot dA is just E magnitude times the top surface area plus the bottom surface area, which is going to be 2 pi r squared. Great. How about Q in? What's the amount of charge inside the surface? Charges are only defined with the slab, and I'm interested in charges only inside my Gauss surface. So it's basically the cylinder, which is the intersection of the Gauss surface with the slab, that carries the charge. So what's the volume of that? The volume of that, this is R, the volume of that is pi r squared times d, the thickness of the cylinder, times rho. So this is not small r, this is capital R, which means Q in, now I can write, is pi r squared times d times rho. So now Gauss's law tells me that 2 pi r squared E magnitude is pi r squared d times rho divided by epsilon 0. Pi is cancelled. More importantly, r squares cancel. E magnitude is rho over 2 d over epsilon 0. And that's on the outside. Z, absolute value Z is larger than d over 2. Very quickly, let me calculate the electric field on the inside. Now, again, if I take a side view, now I need to take a Gauss surface that lies entirely within the slab. Now, will the calculation of the flux change? Remember, the calculation of the flux just depends on the symmetry of the problem. Does it depend whether my Gauss surface is entirely inside the slab or whether it extends to outside the slab? No, it doesn't. So E dot dA is exactly going to be E magnitude times 2 pi r squared again. What will change though? The total amount of charge within the Gauss surface will change. Why? Because now all of my Gauss surface is filled with charge density rho. So this is going to be pi r squared times not d. It's pi r squared times, if I said this is z, it's going to be 2z times rho. So Gauss's law tells me that E magnitude 2 pi r squared is pi r squared 2z rho over epsilon 0. Pi r squares cancel, 2's cancel. So E magnitude is apparently rho over epsilon 0 times z. This is z magnitude less than d over 2. So it's a good idea to maybe plot this as a function of z, my electric field magnitude. Now if I'm outside the slab, electric field is a constant, and its constant value is rho over 2 d over epsilon 0. Am I surprised? Not really. No, I'm not surprised, because I actually asked you to memorize one formula in this course, and it was that if I have an infinite plane with charge density sigma, electric field is sigma over 2 epsilon 0. So what's rho times d? Rho times d is the effective surface charge density here. Good. How about on the other side of my plane, on the other side of my slab? Well, the magnitude of E will be the same, so maybe I should not plot the magnitude of E, but the z component of E. That's more informative. Z component, by symmetry, the magnitude will exactly be the same, but the direction will be reversed. So I'll say the z component is now again a constant, but it is rho over 2 epsilon 0 with a minus sign. And how about what happens on the inside? On the inside, I just have a linear function connecting these two limits. Does that make sense? What happens if I'm exactly at the middle of the slab? What do I expect the electric field to be? Certainly I expect it to be 0, because how much charge I have, I don't care how much charge I have on top of me, I have exactly the same charge at the bottom. So they'll cancel each other, and I do actually go through 0. So z equals to 0, E equals to 0, limit does check. So most probably we have found the electric field for this arrangement correctly. What's our next step? We're going to calculate the potential from this electric field. One quick question before, and we're going to do this in the next hour. One quick question. Can I take V infinity to be 0? quick answer. No, I cannot. Why? Because I actually put charges at infinity. Okay? I cannot do that. There are charges at infinity. So next time we'll actually calculate the potential starting with this electric field. Okay.